In this section, we're going to look at safeguards approaches for spent nuclear fuel. Safeguards approaches in the application of safeguards is facility specific, and that has to do with the physical facility design, analysis of possible diversion pathways, facility management practices and how the operators run things at the specific facility, as well as the role of the State System of Accountancy and Control of Nuclear Materials, or the SSAC. The safeguards approach includes the system of nuclear material accountancy, containment and surveillance measures at the specific facility, the frequency and type of reports that are issued in accountancy reports, and the frequency and type of inspections that are done at the facility. All these things are facility specific. So if we look at our nuclear fuel cycle here to determine facilities with spent nuclear fuel, here we have a picture of the nuclear fuel cycle beginning with uranium mining and going through enrichment, fabrications, operation in power reactors, all the way through to either high-level waste disposal or reprocessing and sending back through the nuclear facility. So spent nuclear fuel originates at nuclear reactors, and then it can be transferred to interim storage or directly to a high-level radioactive waste disposal, or it can go to a reprocessing plant for reprocessing where it's made into MOX fuel, but once it is sent through the reprocessing process, it is no longer spent fuel and it becomes new MOX fuel. So in this section, we're going to take a closer look at the safeguards approach for nuclear reactors, and then we're going to leave an analysis of the interim storage of spent fuel facilities as an exercise for you to do. So first, let's take a look at a simplified nuclear reactor nuclear material flow. It begins with fresh fuel shipment into the facility, and there it goes directly into fresh fuel storage. And then there's a transfer route to the reactor, which is followed by a transfer route to spent fuel storage, and then the spent fuel can be shipped off of the reactor site. Now, obviously, the spent fuel doesn't begin until the reactor, so we're going to focus on what happens after the dashed line there. But since we're talking about the reactor, we're going to include everything that occurs at the reactor in this overview of the safeguards approach. So there are some general concerns when you're applying nuclear safeguards. You have to be aware of the specific facility design and the needs of the operator and how they're going to run the plant. So you have to be cognizant of their needs. You don't want to interfere with the operator's business too much and cause then too many costs. So some thought and planning that can reduce the cost to the operator is definitely appreciated and necessary. And of course, the main concern is the misuse and diversion scenarios of a nuclear facility. And there are two general misuse and diversion scenarios that you're concerned with, and that's undeclared production and diversion of declared materials, which we've talked about before. So let's take a closer look then at specific misuse and diversion scenarios for a nuclear reactor. The first one we'll look at is removal of fuel rods or assemblies from the fresh fuel storage area. And we also want to consider the concealment methods that might be employed by someone attempting to divert or misuse a facility, and how we're going to combat those concealment methods with our safeguards approach. So for removal of fuel rods or assemblies from fresh fuel storage, they might attempt to substitute those removed assemblies with dummy assemblies, or they might falsify records, they might borrow fuel rods from some other location or assemblies and stick them in place of the ones that they took. Another scenario to consider is removal of fuel assemblies from the reactor core itself. Again, they could be substituted with dummies, or there could be falsified records or borrowing from another facility. Another diversion or misuse scenario could be irradiation of undeclared assemblies in the reactor, or use of maybe some sort of targets or something within the reactor core. Some concealment methods for this scenario would be undeclared design changes to allow targets or other assemblies to be introduced to the core from the declared storage location. Another scenario would be removal of fuel rods or assemblies from the spent fuel pool itself. Again, there could be substitution with dummies, falsifying of records, or material borrowing from other locations. One final misuse or diversion scenario is removal of fuel rods or assemblies from a shipment that's leaving the facility, either while it's leaving or shortly thereafter. Concealment methods here could be, again, substituting with dummies, understating the amount of assemblies or fuel rods in the outgoing shipment, and other falsification of records. So let's go back to our simplified reactor nuclear material flow here. And on this figure, we can point out some possible diversion pathways from the fresh fuel storage, from the transfer routes, from the reactor core, and from the spent fuel storage. So we need to be aware of those. And then the next step in our safeguards approach is to set up our nuclear material accountancy system. And first, for that, we'll define our material balance area and then set our key measurement points. So the material balance area for a nuclear reactor basically just goes around the entire facility. You want to make sure, watch what goes in and watch what comes out. But for nuclear reactors, we're going to set key measurement points within that material balance area, not just at the entrance and exit, but several points throughout the facility. There are two types of key measurement points we'll consider: flow KMPs and inventory KMPs. So the flow KMPs obviously go over the flow routes, so we're going to put one at the entrance to the facility where fresh fuel is coming in, a second one on the transfer route from fresh fuel storage into the reactor core, a third KMP from the reactor core to spent fuel storage, and as I'm sure you guessed, a final one at the spent fuel shipment route as spent fuel leaves the facility. Inventory KMPs will be placed at the fresh fuel storage, the reactor core, and the spent fuel storage area. So with our material balance area and key measurement points set, we have our nuclear material accountancy set up. So then we'll move on to containment and surveillance. And for safeguards in general, redundancy is a good thing. We want to make sure if one system fails, the next system picks it up. So we're going to put containment and surveillance over all the transfer and flow routes. And we're also going to put some containment and surveillance over the storage areas and inventory areas. So basically, we want to survey and contain the entire facility. Again, redundancy is our friend with our safeguards. And now, specifically, let's take a look at some LWR, containment and surveillance diagrams. And for LWRs, light water reactors, there are two types of general containment and surveillance plans based on the configuration of the reactor. For type 1 reactors, the spent fuel pool is located inside the reactor containment building. And then type 2 basically means that the spent fuel pool is located outside the reactor containment building. And basically, the only difference here is that when the spent fuel pool is outside the reactor containment building, then you need to add some additional surveillance cameras, whether it's one camera or several cameras, in the spent fuel. When the spent fuel pool is located within the reactor building, then you can put one surveillance system on both the reactor core and the spent fuel pool at the same time. But if they're separate, the spent fuel pool is located outside the reactor containment building, then you need two surveillance systems to go in. So let's first take a look at the LWR Type 1 facility. here you can see, you start with the reactor containment building is the large circle there, and then you can see the reactor core within the reactor building. You can see the steam generator. The spent fuel pool is there next to the reactor core, and you can see the spent fuel canal in between the two. And there's an equipment door on the reactor containment building where equipment can be loaded in, and an airlock for personnel on the outside there. So the first thing we'll do is look where we can place IAEA seals. And we have one here on the reactor core. So when the fuel is loaded and you close the operator closes the vessel containment lid, then the IAEA can place a seal on that to make sure it's not opened when it's not authorized to be open, or without notification that it's going to be open. We can also place a seal on the spent fuel canal gate to make sure no spent fuel is unloaded from the reactor into the spent fuel pool without being declared. And then for surveillance, we have one video camera here that can survey the entire reactor containment area. We can see the reactor core and the spent fuel pool. We can also view equipment that comes in through the equipment door and any people that enter through the airlock. So now let's take a look at the LWR Type 2 containment and surveillance. Here we have the reactor building is the big circle there. In the center of that is the reactor pool and the reactor dome there. Then you can see an equipment door on the reactor containment. You can see the canal gate that leads from the reactor to the spent fuel pool. And then you see an exit hatch there in the spent fuel building. So first question is, where can we place some seals? So here we have a seal on the cable tray and reactor blocks, and that's again to seal the reactor during operation and limit that to be opened only when it's declared by the operator, and so it can be verified by the IAEA inspectors. And then we also have several seals on the equipment door. Again, we like redundancy. So there are several seals there to make sure that door is not opened unless it's declared properly. We can place another seal here on the spent fuel canal, and that's to make sure that no spent fuel can transfer between the reactor and reactor pool to the spent fuel pool without it being properly declared. So then let's take a look at the surveillance measures. And here we see a camera in the reactor building that can survey everything that goes on in the reactor building. When the reactor is opened, when the equipment door is opened. Then we have a camera in the spent fuel pool, and this can survey everything that goes on in the spent fuel pool, where the spent fuel assemblies are placed and what happens when the IAEA is gone. And then we also have external cameras. We have an external camera on the outside of the equipment door. We have another external camera on the exit hatch to the spent fuel pool. And then if there are any other additional hatches in the either reactor building or spent fuel building, we can put another camera to watch those other additional hatches. The final step of the safeguards application is to determine the inspection procedures and schedule. And again, this is facility specific. It needs to be worked out with the operator and meet the needs of both the operator and the IAEA inspectors and any other subsequent verification protocols. If there's an inconsistency found, what's the next step? How do we resolve that? And on what type of schedule do we want to do the nuclear material accountancy verification inspections? What kind of schedule do we want to do the design inspection verifications? All those things need to be addressed and worked out for the application of safeguards. So then if we return to our misuse and diversion scenarios, what we have is very robust and redundant safeguard system that in various places will apply item counting, item identification, application of seals, non-destructive assay measurements, the spent nuclear fuel signatures that we discussed in the previous discussions. And we can also use different types of inspections, simultaneous inspections. We can use some core discharge monitors. Those monitors use radiation signatures that come out as spent fuel comes out of the core. They're very useful in CANDU reactors that are online refueled, so there's not a clear distinction between operation and refueling periods. With online refueling, you don't have to reopen the reactor. The fuel just goes in as the reactor is operating. So a core discharge monitor is basically a radiation detector that sits at the back of the reactor, and as fuel assemblies are pushed out, it can monitor that with radiation signatures. So all of these safeguards measures can address the different misuse and diversion scenarios, removal of fuel rods or assemblies from fresh fuel storage area, from the core or from the spent fuel pool. Also, irradiation of undeclared fuel assemblies or other target materials within the core through undeclared transfer paths. All of these safeguards measures can be applied in different points to help defeat and obstruct these diversion and misuse scenarios. So we have given you some examples of a safeguards approach for spent fuel safeguards at a nuclear reactor for both types of LWRs. We looked at that in a bit of detail. In the written portion, there is an exercise for you to do and basically go through what we did for the LWRs with a interim spent fuel storage facility. Also in the written section, there's more about advanced safeguard techniques for spent fuel safeguards that are under development. There's no exercises based on this section, but it's there so you can look at it and learn about what's in the pipeline and what's being developed and should be fielded in the future. And that concludes the Nuclear Security and Safeguards Education Portal module on spent nuclear fuel safeguards, put together by the Nuclear Security Science and Policy Institute at Texas A&M. I hope you enjoyed it, and thank you very much.